In this section, we're going to look at a couple of application problems. Vectors appear everywhere in applications. Velocity is a vector, acceleration is a vector, force is a vector, tension is a vector. So we're just going to work out a couple examples. We'll start with this one. Here we have a ship's navigator determines the ship is moving through the water at 28.2 kilometers per hour with a heading of 26.3 degrees north of east. So north of east, if we impose like the usual kind of compass direction, with this being east and this being north, 26.3 degrees north of east is a standard position angle. So they've already given us that information, 28.2 kilometers per hour. So we have the magnitude and direction of that velocity. But that the ship is actually moving at 31.1 kilometers per hour in a direction 33.7 north of east. So again, that's another standard position angle. So that's important to realize here. When they say actually moving at, what that means is sort of, I guess, in reference to the land. So moving through the water at 28.2 kilometers per hour, and then in reference to the land actually moving at 31.1 kilometers per hour, we want to know what the velocity of the current is, and it looks like the current is helping out this boat, right, or this ship, because the actual velocity is a little bit more than the velocity of the current, the velocity of the ship through the water. So we have three velocity vectors. We have this one, the velocity of the current. I'll call that VC. And we'll just note that's what we want to find. I'm going to put a little star next to that. That's our goal. And we have VS. I'll call that VS, the velocity of the ship through the water. And then we have, I guess I'll call it VT, the total velocity. Like that's the actual velocity, that 31.1 kilometers per hour that it refers to. And the relationship between these vectors is that this total velocity is equal to the velocity of the current plus the velocity of the ship through the water. Now we want to find velocity of the current, so just look at this equation, right? Like I can do some algebra on this equation. It's a simple equation. If we want to isolate VC, we're just going to subtract VS from both sides, and then we'll get that VC is VT minus VS. So we're going to subtract these vectors. This is a vector subtraction problem, and the way we subtract vectors is the same way we add them. We're going to find components first, and then we'll get the x component for VC by subtracting the x component for S from the x component for T, for VT. And likewise for the y components. Once we have those components, we're back to using Pythagoras and arctan to get magnitude and direction. So let's find these components. We need VT. So first we'll note that VT is 31.1 at 33.7 degrees. And so VTX is 31.1 times cosine of 33.7 degrees. And that's 25.87 or 5.8 or 25.87. And BTY is 31.1 times sine of 33.7. 17.26. Now we'll do the same for the velocity of the ship through the water. That velocity vector they said was 28.2 at an angle of 26.3 degrees. So x component 28.2 cosine 26.3. $25.28. VSY, the y component be magnitude 28.2 times sine of 26.3 degrees. $12.49. Okay, now we've got the components of the given vectors, so we're going to find the x and y components by subtracting the component of the s vector from the component of the t vector. So VCX is VTX minus VSX, or 25.87 minus 25.28, and that gives us 0.59. And the y component, VCY, is VTY minus VSY. So that's 17.26 minus 12.49. $4.77. Now we have our components, and once we have our components, we're ready to get magnitude by using Pythagoras and the direction by using arctan. Notice both these components are positive here, so this is quadrant 1, which means the vector we want is the reference angle. We won't need to make any adjustments to that. So for magnitude, square root of 0.59 squared plus 4.77 squared at 4.81, and theta is arctan of 4.77 over 0.59. $82.9 degrees. So the velocity of the current is now so there's a context to this problem, right? This is a vector velocity, or velocity vector, and it has units. And when we attach units to a velocity vector, it's always the units always go on the magnitude. So this is 4.81 kilometers per hour at an angle of 82.9 degrees. So a lot of physics applications will involve forces or tensions. A tension is a force of an object that is on equilibrium. So, you know, an object's on equilibrium or is in equilibrium if it's not moving, right? So like that means that the forces that it might be acting on it are equal and opposite in direction. Like the x components sum to 0 and the y components sum to 0. If they didn't sum to 0, if the total of the forces was not 0, that means that it would be moving, right? There would be a force acting on a mass, and it would move. So if something's not moving, that means it's in equilibrium. Here we have a 225 kilogram sine is supported by a cable here, and we're going to find the tension in the cable. So this is exerting 225 kilograms downward. And we want to know what is the tension in the cable. So there's a tension overall, right, exerted along this direction. I'll call this T. It's a T vector. And it's 140 degrees from this horizontal on this side. So if I kind of sketch this out, I'm just going to sketch out what this vector looks like in the plane. It's 40 degrees up from this negative x-axis. And so that means this is at 140 degrees. Here's our T tension vector. We know that we have that tension vector is sort of canceling out this vector here, this downward vector, 225 kilograms. So if this is an equilibrium, since the sine is exerting a force downward, 225 kilograms, then the y component of that tension vector has to be 225 kilograms upward. So we're going to use that. We're going to use that concept to help us set up an equation. So again, the sine is exerting 225 kilograms down. And that means that the y component of the tension vector is 225 kilograms upward, right? Positive 225, so that means it's going upward. We can just use this. This is all we need in order to solve this problem, because we know what the value of 220 of the y component is, and we also know that the y component is going to be found by taking the magnitude and multiplying by sine of theta, and we know that theta, right, is equal to 140 degrees up there. So we know that, plugging in the known theta and the known y component, we get 225 is equal to the magnitude times sine of 140 degrees. And in order to find the magnitude, we need only divide by sine of 140 degrees. And so this tells us that the magnitude is 350.04. So 350.04 kilograms. Now, since I already know the direction was 140 degrees, we just found the magnitude. That means we have the vector. This tension vector is 350.04 kilograms at 140 degrees.